thank you very much for the introduction and for the invitation to come and give the Higgs Lecture this evening. As I sat listening to Peter talk, I couldn't help but spot a typo on the first slide there. But as I give the talk, again, and you hear the talk, I hope you'll forgive me and understand why, when I wrote it, February 2016 was very much on my mind. And so you'll see that as we go along. So we're going to talk about gravitational waves, and so we're going to talk about gravity. And in the universe, in terms of all the things that we understand, in terms of the forces that govern all the interactions in physics, there are really four fundamental forces, and there they are on this slide there, and gravity is one of those. And in many ways, it's an anomalous force. And of these forces, two of them are ones that probably are familiar to pretty much everyone in the room from everyday life, of which gravity is one. And we're all pretty familiar with what gravity does and what it feels like as a force. The other force in that list is the electromagnetic force that we're typically familiar with. We understand what magnets do, again, the sort of pull of magnets as they're attracted to one another or to metal. The other two forces, the weak force and the strong force, are very important and they cover very important parts of physics, but on the whole, we don't really experience those or their effects so much in everyday life because they actually act typically over very short distances inside atoms. So those we tend not to think about in everyday life, but gravity and the electromagnetic force we do. And up the side here, I've put the sort of relative strength of these different forces. And by far the weakest, by far, is gravity. And it doesn't seem like that to us because it's so fundamental to how we experience the world. It's what holds us here on the surface of the Earth. And so gravity actually feels to us substantive. We kind of know how it feels. If we jump up, we come back down. If we pick up an object and let it falls to the ground. So gravity is very real. And we kind of know how that feels, what that force feels like. So nominally, in your mind, give that a strength of 1 in some arbitrary units. Then if we look at the other forces and their strengths compared to gravity, they are all phenomenally stronger than gravity. Many, many, many tens of times stronger. Again, scientific notation there, but 10 times stronger would just be 10, 100 would be 10 to the 2, 1,000, 10 to the 3, so 10 to the 25 times stronger than gravity is hugely strong. And that's true of all of them. Gravity is by far the weakest, but it is exceedingly important. Again, if we think about the electromagnetic force, if we take our fridge magnet and we hold it up to the front of a fridge, the electromagnetic force beats gravity. It will suck onto the front of the fridge. If, however, we pull it a bit further away, let it go, it will fall, and gravity takes over. And gravity wins on large scales because gravity only has the one sign. All particles of mass attract one another. So the forces add up, and so on large scales, gravity tends to be the winner. And that's because, of course, in the electromagnetic force, we can have plus and minus charge. So on large scales, those effects can cancel out, but gravity on large scales, on the scales that we're interested in, is exceedingly important. It's responsible both for the birth of stars and for the death of stars. Perhaps for the fact that we exist at all, we're again far out in the cosmos, clouds of dust and gas pulled together under the influence of gravity eventually formed the stars, the galaxies, and so forth. And how objects behave under gravity is described, again, by Newton in his law of gravitation. And it's relatively simple in form. Newton's law of gravity says if you have two objects, two masses, they feel an attractive force, and how much they are pulled together depends on their masses, their relative masses, and how far apart they are. And that's a relatively simple formula, and it describes pretty well how many objects move under gravity. If you want to calculate how orbits move or projectiles move, the law of gravitation works pretty well. But it does have a very uncomfortable feature, and that's instantaneous action at a distance. In other words, if we have our two masses and they are separated by some distance, feeling an attractive pull, if an object, one of those masses, moves and the distance between it and the other mass changes, the force between them changes, and it changes apparently instantly. And so that tells us if one of those masses is us here on Earth and the other mass is a star some large distance away, there's a gravitational attraction. If that star moves its position with respect to us here on the Earth, we would, in principle, know instantly, because the gravitational pull here would change instantly in Newton's theory. And that's very uncomfortable to think we could get information instantly about something happening a very, very long way away. And of course, that isn't correct, and it took Einstein, with his special theory of relativity, to come along, and special relativity tells us that information, no information, can be carried faster than the speed of light. And that includes gravitational information. So actually, special relativity tells us that there must be travelling gravitational signals. There must be gravitational radiation. No matter your favourite theory of gravity, special relativity tells us that. But it's general relativity that really mathematically explains how mass and space-time interact properly, and predicts the existence mathematically of gravitational waves, travelling gravitational signals. And I've put up a couple of pictures here. Again, general relativity in 2015, we had the 100th anniversary of the theory of general relativity, and actually 2016 was the 100th anniversary of the prediction of gravitational waves, these travelling gravitational signals. And the pictures here you'll recognise very quickly, both of Einstein. Again, I took from a talk actually at a meeting here in January this year about relativity and gravitational waves and some of the history. And I believe this is Einstein visiting King's in 1921. And this is Einstein actually in Glasgow, receiving an honorary degree in 1933. And in both cases, I think, he gave talks on relativity, on his theories. And the cover here, you can see the origins of the general theory of relativity, again by the University Press in Glasgow at that point. And in fact, if you visit the physics department in Glasgow, you'll see Einstein's notes on the wall, again with his handwritten annotations of those lectures. And this is now long enough ago that there's pretty much nobody left in Glasgow who was around at that time and remembers the lectures. Rumour has it they were pretty incomprehensible and nobody really understood very much, because general relativity in truth is a very mathematical theory, very complicated theory. But I like these pictures for a number of reasons. It's nice to see Einstein again in my home institution there with the connections that we have to gravitational waves and the theory. But I like this picture for another reason. He was there getting an honorary degree, and again, there were a number of other people there in that picture, one of them the principal of the university, I think, at the time. Other people, distinguished men receiving honorary degrees, one of them a man of the cloth, I think the Archbishop of Armagh and Primate of all Ireland is one of those folks. Monsieur Edouard Herriot, former Prime Minister of France, it says at the bottom. And yet today, if we took this picture out into the street and showed it to the public, I think probably the only person they would instantly recognise in this picture is Einstein. And so it cheers me up every time I see this picture again, and that all this time later, these many decades later, the person in that picture with the lasting influence on the public imagination is actually the scientist in the picture, and one who worked on very fundamental science at that. And so in these dark days, as they sometimes are at the moment, this picture cheers me up enormously. So Einstein, again gave various talks, was on a tour explaining to people his theory, of which, again, gravitational waves were a part. But if you look at the times there, this is 1916, 21, 33, many decades, again, separate us from then. And there's a long story in between times to get to where we are. But to give a picture, again, a sort of non-mathematical picture of what general relativity tells us in terms of mass and gravity, if we think of this grid as marking out positions in space, where there's no mass, we see these nice regular markers here. With some mass, we see distances in space appear to distort. And what general relativity tells us is geometrical, that mass curves the space, distorts the space-time around it. And once distances in space-time are distorted, then matter must follow those. Mass then follows those distortions. So matter, mass, curves space-time. Space-time, when curved, then guides the motion of mass through it. And that's really what general relativity says in a geometrical way. That's what the maths tells us. But it took a long time to get from the theory of general relativity to the detection of gravitational waves, one of its big predictions. And in general relativity, what general relativity tells us is that these travelling gravitational signals, these gravitational waves, are produced when we have some mass that moves in an asymmetric way, some mass sort of wobbling, some mass suddenly changing its position, and we'll talk more about that, changing the curvature of space round about it, and those ripples in the curvature of space spreading out. However, originally, again, in the sort of history of general relativity and this prediction of it and these travelling gravitational signals, there was a lot of uncertainty about whether this really was some mathematical artifact of the theory or whether there was a real physical meaning to this prediction, whether this had a measurable physical effect that we actually could sense. And that went on for a long time, many decades, and there was a turning point. In 1957, there was a meeting in the US, the Chapel Hill meeting in relativity, where really there was a very significant point where, in fact, Felix Pirani and Herman Bondi, who at that point I think were here at King's College, Felix Pirani gave a talk, and people came to the realization that there was a real physical effect, that these mathematical waves could cause measurable changes in the distances of objects that could actually be measured. And that was a really significant point in the field. At that meeting was a scientist called Joe Weber. Again, in listening to those discussions, again with another scientist, John Wheeler, came to the realization perhaps these could be measured and really started the experimental field to try and detect gravitational waves. Coming out of this, again, very, very important discussion, and again, the history of all of this is actually described rather nicely. There's a book I would recommend called Travelling at the Speed of Thought by Daniel Kennefick, who talks about the history of this. Again, but you can see it took a long time. It took until the 1960s before people really thought seriously about how to build experiments to measure these gravitational waves. So, we'll take the experimentalist's view in this case, because we're interested in the measurements of what they tell us, that a flat, empty universe will become distorted with the presence of mass. Space-time will be distorted. We can think of that curvature in space caused by the presence of mass as gravity. So in this picture, if we come along, we add a second object to our universe, it will appear to be attracted to the first one. It will roll down that curvature. That curvature we can think of as gravity. If this mass suddenly changes its position, the curvature around it changes. There are travelling gravitational signals sent out, ripples in this curvature, and those ripples, changing gravitational fields, are carried with them. Those are our gravitational waves. We said gravity was responsible both for the birth of stars and the death of stars, and in terms of the death of stars, again, one of the sources of gravitational waves, which needs huge masses with huge accelerations, are stars reaching the end of their life. So, if we have a star, on the whole, throughout its life, it sits there balanced with gravity trying to cause it to collapse, and that force of gravity being balanced by thermal pressure, with the centre of the star having hydrogen fusing into helium, holding the star up. In that simple picture, of course, what happens when the fuel runs out? Gravity is relentless, gravity wins, the core of the star collapses down, squashes together the atoms, again forces the protons and electrons in the atoms into neutrons, again potentially forming what we call a neutron star at the end of that process, or perhaps even a black hole, where the mass of the star has collapsed down into a region of space where gravity is so strong that nothing can escape its gravitational pull. In that process, there's a large amount of mass that very suddenly changes its configuration. It suddenly changes the curvature of space-time around it and sends out ripples across the universe. So by being able to study the gravitational signals coming from that kind of event, we can get different information than we can by looking at the outside, typically the bright flash we see in a supernova explosion. Because what I've told you, everything I've told you, we deduce on the whole from looking at the outside of that event. Excuse me, we see the optical flash and we try and deduce what's happening inside. The gravitational signals would come from the core collapse itself, carrying with them very different information about what's happening inside the event. Again, rich physics that we do not totally understand. At the end of that process, we said we can form perhaps a neutron star. And this picture here is of the Crab Nebula, a supernova remnant from a star that exploded a long time ago, throwing off its outer layers, leaving this beautiful glowing nebula. In the middle of that, we believe, there is a neutron star left over from a supernova explosion. And that neutron star, roughly 10 kilometers or so across, is spinning. And it has some electromagnetic field left. Any charged particles caught in that are accelerated and give out radio signals. So as this neutron star spins, it's like a lighthouse of radio signals. And every now and again, that lighthouse beam of radio signals passes us on the Earth, and we see a blip. If this is not a perfect sphere, the neutron star, if there's any lump on its surface, as it spins round, it traces out a dent in space, changes the curvature of space, and sends out continuous signals, gravitational signals, out across the universe. We would very much like to detect those signals. Neutron stars are objects, again, with matter under densities and pressures that we cannot simulate here on Earth. And so there's matter really at the extremes of what we understand. Again, and that makes different predictions depending on what material the neutron star is made of, what state it's in. There are different predictions about the size of any lump that can be sustained on the crust of the star. In other words, making predictions on the size of any gravitational wave signals that could be produced. So by detecting the gravitational signals, we can actually, in principle, learn about what the material, neutron star material is, using space as a laboratory. If we have pairs of neutron stars, a binary system, they're caught in one another's gravity, rolling round in space, changing the curvature of space around them, again sending out gravitational waves out across space, either a pair of neutron stars or a pair of black holes, as we'll talk about. As they get closer and closer together, they get faster and faster, losing energy, sending out that energy, spiraling in until eventually they collide and give out a burst of gravitational radiation. Those kinds of systems, again, with super strong gravity, especially in the case of black holes, are right at the edge of what we can, again, study with general relativity. We know that general relativity cannot be the full picture describing gravity, describing mass in the universe. As I'll point out later, we simply know that can't be true. Can we use the gravitational wave signals to push to the edge of what we can do and predict with general relativity and understand gravity in super strong regions? In a binary system, a pair of stars like that, there's another important point in the history of gravitational wave detection. A pair of these, where one of these you can see is a pulsar, is giving out these jets of radio, again a very characteristic system there. There's a particular system called the binary pulsar, studied by these scientists here, Russell Hulse and Joe Taylor, looking at the radio signals, again coming from the pulsar there using the Arecibo telescope. They studied the orbit of this star system to see how the orbit was changing over time. And it's a very famous result, again, where when they studied the behaviour of that star system, that binary pulsar, again, you can see from 1975 up to, I think, the last measurements, again, about 2000, in the early 2000s. And they saw the system getting closer and closer together, speeding up in terms of closest approach, and losing energy as it did so, exactly in agreement with the predictions of general relativity if the system was radiating gravitational waves. And the reason, of course, they probably look so happy here is they got the Nobel Prize for this result as really conclusive but indirect evidence that gravitational waves existed, absolutely consistent with them being produced by this system. And everything I've talked about so far in terms of studying gravitational waves and how they're produced is just part of the story, part of the picture. This plot here, again, is, again, along the bottom here, you can see frequency, up the top wave period, again, how fast these oscillations, these gravitational waves are happening. And there's a huge spectrum that goes from waves with a period of milliseconds down to waves with a period of the age of the universe. And all the sources I've talked about so far actually are just at one end of this spectrum. And in the same way that electromagnetic astronomy has a huge spectrum of wavelengths for us to study, from the microwave to gamma ray, X-ray, infrared, optical, covering a huge spectrum, the same is true of gravitational wave signals. So those merging binary neutron stars and black holes, those pulsars, they're actually all just up the right-hand side of this plot. And in the same way that we have a range of telescopes to study different electromagnetic signals, we need a range of different detectors to detect gravitational signals. And the ones I will talk mostly about, again, are the ones here at this end, again, with these kinds of sources. But there are other exceedingly exciting sources for which we needed different kinds of detectors. I'll talk a little bit about some of those, but I'll concentrate on these ones here. And the last of those sources, again, with the detectors I'll talk about on the ground, are pairs of black holes colliding. And this little animation here, again, shows the distortion of space-time, this little animation showing two black holes spiraling in to collide, getting closer and closer together until eventually they merge. The event horizons, the point of no return of the black holes merge to form a new black hole. And I'll run that animation again, because underneath you'll see a cartoon of the gravitational wave signal that we expect from this kind of system far out in the universe. This is what we expect here on Earth if we try and measure the distance between 2 points here on Earth changing due to two black holes spiraling in to collide, getting closer and closer together, eventually actually merging to form a new black hole, and then that black hole ringing down, as we say, wobbling slightly afterwards. And you can see it's a very characteristic signal as space-time distances are stretched and squashed back and forward as these gravitational ripples arrive here on Earth, caused by this system far out in the universe. It's a very characteristic signal indeed, and that's the signal, again, a signal of that type that was detected, the first detection of gravitational waves, announced in February 2016, which you can see why February 2016 was very much in my mind, again, when I was thinking about this talk. In fact, it was 11th February 2016, and we're almost about to reach the anniversary of that first detection in a few days' time. And this plot here is a plot from the paper announcing that first detection. And you can see there are two panels, the first one of which shows the signals arriving at one of the detectors of the LIGO project, and the detector itself is in Hanford in Washington State. The other detector located in Livingston, Louisiana in the US. And you can see that very characteristic signal, that wobbling. This is red shows the trace from Hanford, blue from Livingston, and in this plot they're overlaid, so you can see that same signal arriving in both detectors. The top signal here is the data from the instrument, the detector itself, only very lightly filtered. Again, it's the data from the instrument. And underneath, the kind of best fit, again, from our models of what these black holes spiraling in do, shaking slightly the fabric of the universe. That very characteristic chirp, as we call it, getting faster and faster, these peaks getting closer together as distances are stretched and squashed till the black holes merge. And buried in that are the properties of the system that produced it. And we can tell a lot just from what's encoded in that signal. And this is, in many ways, a remarkable first discovery. It's a discovery of many, many firsts, and I'll talk about a few of those. It verifies those predictions of Einstein, again, that early on were controversial, again, that people perhaps, again, really were not confident, had real physical meaning, could actually be measurable. This is the first direct detection of gravitational waves. The first gravitational observation, really first observation at all, I think, of two black holes colliding and the birth of a new black hole. Detected, again remarkably, the 100th anniversary year of general relativity, because the detection itself was made in September 2015 and announced in February 2016, and I can talk about what happened in those intervening months, in the 100th anniversary year of the prediction that such signals should exist. There's that in-spiral face, the black holes spiraling round, getting closer together, merging to make a new black hole. And there's a lot of information encoded in the exact shape of that signal. From it, we can get the distance, how far out in the universe those black holes were when they collided. And you can see here, this is the abstract from the paper, 410 megaparsecs, which is equivalent to 1.3 billion light years, a light year being the distance that light travels in a year. So that collision really happened 1.3 billion years ago, sent out its signature, rippling through space to arrive with us on September 14th in 2015. We can get the masses of the two individual black holes spiraling in, one about 36 times the mass of the Sun, the other about 29 times the mass of the Sun. We can get information about how the black holes were spinning and how that final black hole was spinning, the black hole that was formed. We can tell that that final black hole was about 62 times the mass of our Sun, but squashed into something that was about the size of Iceland, about 366 kilometres across. We can tell the final black hole was spinning about 100 times a second, that a point on its event horizon was travelling as it span round at nearly half the speed of light. That final black hole itself wasn't a perfect sphere, because of its spin it was squashed about 20% smaller in one direction than it was in the other. And all of that information is encoded in that chirp, in that stretching and squashing of space that arrived here on Earth. All of that we can get from that signal. And in fact, that was the first of two announced detections. Again, the first detection, as I say, made in September 14th, 2015, announced in February 2016. And then in June last year, again, there was a second announcement again, of a detection of another black hole in spiral, another black hole collision, which was detected 26th of December. It's called the Boxing Day event. 26th December here in the UK, actually on Christmas Day in the United States. And in between those, again, as these detectors ran, there was another possible event, one that happened on October 12th, smaller than these two signals, so one that perhaps wasn't big enough for us to be claiming it as a detection, but consistent with another black hole collision. For many reasons, this was remarkable to people working in the field. We did not expect this and we should note, this is the first time we turned on these big new detectors, what we call Advanced LIGO detectors. They had really just started. In fact, that first signal came in a couple of days when the instrument, before we were officially declaring ourselves as having started taking data. The instruments were running. They were all running quite happily, and suddenly that signal arrived, and it was a big surprise. When we look at the different signatures of those events, you can see that the systems have different properties. There's that first signal, those cycles of the black hole spiraling in and suddenly combining. There is the Boxing Day event. We saw many more cycles before those black holes collided. And again, their properties of that system are encoded in that signal. And the one in between, again, the smaller signal, again, looking slightly different again. And from that, we extract the properties of those black holes. And when we look at what that's done to what we know about black holes in our universe, it already changed our picture immediately. On this plot, up the side here, you can see number of times the mass of the sun. And from all the previous electromagnetic studies of how matter appeared to be moving around something that suggested there was a black hole there, the black holes all clustered in kind of this range, again between, say, 5 and up to 20 times the mass of the sun. The first black holes we detected using gravitational waves were these two here, again at 29, 36 times the mass of the sun, into a huge black hole, 62 times the mass of the sun. That was unexpected. We did not expect that. Again, and it already starts to have implications about the astrophysics of the stars that produced the black holes. It really was unexpected. So unexpected, we were not searching for this at all. We were, if anything, searching for black holes this size. So we have already, with the first detection, started to fill in the family tree of black holes out in the universe. Again, in February last year, when we made the announcement, again, you've seen this is something that people had been working on, trying to do since the 1960s. It took a long time to build instruments capable of doing this, and I'll talk about why. Again, it seems like a long time ago in many ways, February last year. A lot has happened in the world since then. What was fantastic, I think, about this discovery was it was science's front page news, and science's front page good news. Again, there was no epidemic, there was no great disaster. There's nothing but a good news science story. Again, in hundreds of newspapers around the world, you can see this is just a small fraction of the coverage that was there. I think there were over 900 articles, again, front pages, covering this story. Anywhere from Spain to Germany to Japan, South America, the US. I think it was fantastic and actually quite overwhelming to see the interest and the appetite internationally for science and for this kind of science, for such fundamental studies. And it took a lot of people, again, very topically, 1,000 scientists from 14 countries, again, of course, including scientists here in Kings, to do this. This was not something that any one nation did on its own. These big scientific challenges require international collaboration. And so it was a fantastic time, again, quite amazing to live through. But you can't please all the people all the time. This is what Private Eye had to say on the subject, for those of you who know Private Eye magazine. The headline, most important scientific discovery for a generation. A huge black hole opened yesterday in the public's understanding of what the latest scientific breakthrough was all about. No light was shed at all by a huge, dense mass of newsprint that collapsed in on itself as it attempted to explain the importance of gravitational waves. The amount the public understood about the subject was so microscopically small that first instruments could not detect it. But after refinement, the comprehension level measured less than a billionth of an atom. Said one hurt astrophysicist, this could be the most significant lack of understanding since the last thing the public didn't understand. However, a member of the public was quick to congratulate the scientific community. Look, we're very happy that they're happy, and I'm sure the whole gravitational wave factor thing will help us defeat the Klingons and destroy the Death Star, or is that the other one? Anyway, that was a good bit. So we should not take ourselves too seriously in the fantastic job that we're doing in getting this coverage, and it was a salutary reminder that we have to work hard to try and explain what we are doing, why we're doing it, what its importance is. Not least because this article was actually sent to me by a senior member of my own funding agency, who fortunately has a sense of humour. But it is a reminder that we, again, very topically in the times that we live in, have to try hard to explain science, again, and the importance of what we're doing. So, in that vein, what are gravitational waves? They are a strain in space. They're a bit like ripples on the surface of a pond. They're produced and they travel out across the universe, causing it to distort. Why do we care? It's a completely new way to study the universe. We have already studied objects that we might actually not see, as I will talk about, any other way, giving out no light, no electromagnetic, no other detectable signals, sensing only their gravity. So how do we do that here on Earth? Well, those physical effects that we mentioned, again, that were so important, again, from Pirani and Bondi, if we look at a patch of space, we pick our favourite patch of space on the board here, and gravitational waves pushed far out in the cosmos have been coming in, hit the solar system, hit us here on Earth, pass through the board. If we try to measure the distance between points on the board, this is what we would find. They would be distorted. They would be stretched in one direction and simultaneously squashed in the other as a gravitational wave passed through. However, this is greatly exaggerated for effect. How much would things be stretched? Well, for masses, points on the board like that, objects separated by about a metre, a typical gravitational wave would stretch them or squash the distances by about 10 to the minus 22 of a metre. For scale, just as a reminder, the width of a human hair is about 50 microns, 50 times 10 to the minus 6. Size of a typical atom is about 10 to the minus 10 metres. 10 to the minus 22 metres, as you can see, is many orders of magnitude smaller than the size of an atom. So not very much, and that is what has taken all the time to build instruments capable of doing this. They're based on something that's familiar from undergraduate physics experiments, a Michelson interferometer, where we take light from a laser. We split it into two, bounce it off two mirrors, those are our markers in space. Look at how the light recombines, and by looking at how that light recombines, we can sense how these mirrors are moving. Again, quite simply, we think we use the fact that light's a wave. If, as those light waves travel out, they travel the same distance in each arm, come back, we have two peaks adding up, we get a bright spot. If, on the other hand, the gravitational wave has passed by, stretched one distance, squashed another, then the light waves returning can cancel out and we get a dark spot. So quite simply, we look at the brightness of the light here to search for changes in the position of those mirrors. However, again, as you might guess, it's still tough if we look at the numbers. If, from general relativity, we calculate the strength of this effect that we expect, say, from those black holes far out in the universe smashing into one another, and how much we expect them to stretch or squash one of these arms, we can calculate the strength of the gravitational waves. Say they take some arm of length L, stretch it by some small amount delta L. What's going to happen? Well, H is less than about 10 to the minus 22, the strength of the wave. That we can calculate from the astrophysics. If then we built an instrument with a metre long arm, we would only see one of these mirrors move, again by our 10 to the minus 22 of a meter. Tiny, tiny amount. It tells us we need to make L big. We need to build huge instruments to make delta L, that measurable distance, big enough that we can measure it. So in building these instruments, I won't talk about the technology, but I draw these stick diagrams to show how the instrument works. In truth, reality goes in this direction, and Peter alluded to this at the beginning of the talk. Reality involves phenomenal physics and engineering to build instruments capable of making these measurements. The two instruments, again, that are running currently, again, that made those first detections, the LIGO observatories, there's Hanford, there's Livingston in the United States, and they are located in the United States, but actually part of a global collaboration, and again, with many countries involved. The group that I'm from, groups Cardiff, Birmingham, here at King's, Sheffield, elsewhere in the UK, and around the world working together on this. To give you a quick overview of what these sites look like, these are large instruments. They have 4-kilometre long arms, again, in these detectors. There's that central station where the laser and the beam splitter is, and the Hanford site, excuse me. And you can see it's about the size of a supermarket, concrete covers going out with the laser beams fired along it. This is the Livingston site. You can see it's a very different site. It's in Louisiana. It's literally in a swamp. These beautiful pools, again, up the sides of the detectors. Again, if it turns out if you dig a hole in a swamp, it fills with water. These pools are there, again, earth was dug out to build banks, to put the detector up, again, on banks above the flood level in the swamps. They're very different sites, both very beautiful in their own ways. And doing big science like this requires a bunch of challenges, again, that are often not obvious when you think about what we're trying to do. These are all pictures from the Hanford site, in fact. You can see it's actually in a Department of Energy nuclear reserve in the US. Again, when you drive there, you pass nuclear domes, nuclear reactors. It's actually, I think, where the material was made for the atomic bombs that were dropped in the Second World War, but now really used for medical nuclear purposes. This is burnt tumbleweed from a wildfire, again, that actually burnt right up into the arm of the instrument, to the concrete cover there. These are my colleagues standing thoughtfully on top of the centre station, looking at the wildfire in the distance, contemplating what to do. You can see the detector itself actually acted as a fire break. There's the tumbleweed on the other side is just fine, the fire burned right up to the instrument. This, well, it's on a nuclear site, and so every now and again there's a security drill. In the middle of the night one night there was a security drill. Security guard got up, got out, jumped into his car, set off across the site, forgot there was a 4-kilometre long scientific installation in the way, and sadly drove right into the beam tube cover, which is why those concrete covers are there. You can see it's very important. He was fine, you'll be glad to know. The instrument was fine. His car was not terribly fine. But these are some of the unexpected challenges, again, that people often don't think about in doing astronomy, and it's true for all big science projects. It requires a whole set of skills in interdisciplinary areas that one might not necessarily think of in advance. The LIGO detectors are part of a global network for scientific reasons. It is important we have not one or two, but actually a network of these instruments. And in fact, the LIGO instruments were the first in their advanced form to turn on in 2015. Virgo, again, a European detector, will turn on very shortly, in fact, in the next couple of months. And soon after the detection was announced in India, the Indian government agreed to host another LIGO detector in India, and our Japanese colleagues are building a detector in Japan, well advanced, called CAGRA. And of course, for many years, we in the UK have, with our German colleagues, run a smaller instrument that was an essential test bed for the technologies that were installed in LIGO, making us partners in the Advanced LIGO project to make these first detections. And we need a network to do the science. And because these instruments are not like telescopes that you can point at an area of the sky. They have some sensitivity to the whole sky, which is good, but it's also bad, and it means we don't know where necessarily signals are coming from. We have to use timing and triangulation. Essentially, if a signal from some system's coming in this direction, it will hit this detector first and then the other, giving us some crude information about where it's coming from. We want to know where it's coming from because some of the things we're interested in are unlike those black holes. They will produce light, the supernovae, the neutron stars colliding, and we want to know where they are so we can ask our colleagues with telescopes to look in that part of the sky. And in fact, that is what was done for the first detections for the black hole signals. We take data from the network, we do a fast look to see if there's anything there. Those first detections, again, I think within 3 minutes, we knew we had a signal, a potential signal there. Estimate where in the sky it's coming from. Again, a lot of this is done automatically, but again, currently it still phones a human to double check things are okay. Send that information out. However, with just 2 instruments, we're asking people to point their telescopes at a few hundred degrees in the sky. That's an enormous area. Adding the Virgo instrument in Europe, that improves a lot, and it will improve further with the addition of the other instruments. For that first detection, this eventually was the portion of the sky that we said, well, it's coming from somewhere in there. It might be over there, but it's really most likely in there. That's a huge portion of the sky to ask someone to point their telescope at. And in fact, this is the first information that we sent out, saying, here's this swathe of the sky the signal might have come from, could you look? Again, and our astronomy colleagues with whom we had a memorandum of understanding worked hard in the optical, the X-ray, the radio, and this blow-up shows they tiled that huge patch of the sky to look hard for an electromagnetic signal. Now, since this was 2 black holes, in fact, one might expect it to have none, and indeed they didn't see anything, but they worked hard in a way that's not efficient to use their telescopes to look. It's not ideal. We really want a network of detectors to be able to squeeze down the uncertainty. This is the sky again, with those 3 potential, two announced and 1 potential candidates, just with the LIGO instruments. If we add 1 more, if we add Virgo, for that detected signal, the uncertainty shrinks hugely. It makes an enormous difference. So a network of detectors is incredibly important. So where are we and what's coming next? Well, the results I showed you came from that first run of the instruments, which again was September 15 to January 2016. It was just a 4-month run. The instruments were then turned off and for improving, and we always knew we would do that. In fact, we did not expect to make detections in that first observing run. We planned to run for 4 months, try everything out, turn the instruments off, and improve their sensitivity, because for those first detections, they were still they were much better than the first instruments we had, but still a factor of 3 or so away from where they should be. So the detectors were turned off for most of last year. In November last year, we turned them on again to start more searches, again with slightly improved performance. That's currently in progress. And as of January this year, we want, again, both instruments to be running at the same time. We've taken, I think, as of January 23rd, 12 days of coincident data with them collected. There was a break over Christmas. And during that time, there's 2 event candidates that have been identified and again sent out to our astronomy community, again, who've signed MOUs, again to look, to point their telescopes and see if there's anything. We should note the asterisk, again, we have an agreement that will do that with a kind of false alarm rate threshold of 1 a month. So we would expect once a month to send out a trigger or so to our colleagues. So that's kind of where we are at the moment, and that data taking is ongoing. What do we think is going to happen? Where do we think we're going? Well, now that we have seen these black hole collisions, that actually has improved people's understanding of perhaps what we might expect going forward. So, as we go on, there's that first observing run that was complete in January. We're now in the second observing run. Along the bottom here, is the searched space-time volume of the universe in which we're searching for signals compared to what was done in '01. Up the side here then is when we've searched some volume of the universe, how many events might we expect? How many black hole collisions might we expect to detect? And you can see there's uncertainty. This pink band here is what we want to focus on. So it depends how well we do in improving the sensitivity of the instruments. And it depends, again, how often these events really happen. And still there's some, spread of uncertainty in that. But up the side here, the numbers start to be interesting. In the second run, we see a 10. As we go forward, 100. And again, I think this is much more than we really expected when we turned on our detectors. These merging black holes are now a key target for future gravitational studies, again, in a way that we really didn't expect. At the same time, we're also searching for those colliding neutron stars, those pulsars spinning. Things, perhaps most excitingly, that we do not yet understand. It cheerfully says they're unmodelled transients. Sources that we simply don't understand yet. And there's, I think, good reason to think that that is an exciting prospect. So, again, we're working on improving the sensitivity of those instruments, running them for longer. We'll work with the network, again, when it comes online. And it really is new astronomy. It is a completely different way to feel the gravitational signals from the universe coming in. However, nobody ever met an astronomer who really felt they had a big enough telescope, who could really see far as they really wanted to, and we are no different. This is the start of a new field. So we are already working hard on the technology to upgrade those instruments, to make them even better, to search further out in the universe. And that is happening, again, in an international, coordinated way. We expect soon we will make regular detections. But you will remember I said everything that we have talked about so far is just part of this whole spectrum of gravitational wave signals. And there are exciting sources that we will not be able to detect with these ground-based detectors. Things like the supermassive black holes that sit at the centres of galaxies, again, that we believe are out there. We will not be able to detect those, again, for technology reasons on the ground. For that, we need to put detectors in space. There's a picture of the Andromeda galaxy, again, at the centre of which we think there is one of those supermassive black holes. There's a picture of the Mice Nebula, which again we believe is two galaxies in the process of merging. And there are many galaxy simulations that are done of galaxy collisions, and this is one of those. Two galaxies colliding, and if we stop there, you'll see that looks, in this case, this model looks a lot like the Mice Nebula. There's a whole family of these out there. If we keep it going, we'll see the galaxies don't just pass through and go on, they actually merge. So what do we think is happening there? Well, if we run that again, there's our colliding galaxies. They get caught. If we strip the stars off, look at what's happening. There's supermassive black holes at the centres of those galaxies, and they get caught in one another's gravity, with the supermassive black holes spiralling around one another, taking the whole galaxy with them, until eventually those supermassive black holes collide. That would be a phenomenally exciting source to study. It's not one that we can do here on the ground. For that, we do need to put detectors in space. This is, again, not a fast business. This is a picture from just over 20 years ago of the first LISA symposium held at Rutherford Appleton Labs in 1996. Many things have changed in that time. Apparently my haircut has not. I'm actually there. I was a bit shocked to discover. And this is, again, many folks who work in the ground-based community also have interests on the space side. So 20 years after that, where are we? Well, actually, although that was the first LISA symposium, LISA being Laser Interferometer Space Antenna, the idea for a space-based detector predates even that, again going back to the 1980s or maybe even earlier. And there's been an evolution in the ideas for what a space-based detector might look like, but based around the same sort of concepts, using lasers to monitor the positions of points in space, where in this case the points in space are in separate spacecraft, with laser beams fired between the spacecraft. A sort of 3 spacecraft mission settled down, again in the mid-90s, but again the technology is challenging, so to put such a mission in space, there was a need people identified for a Pathfinder mission to test some of that technology, and that proceeded, again, alongside what has, again, for a long time been a joint European-US mission. NASA, for a while, again, felt they couldn't be involved. It was formulated as a European-only mission. But all that time, Pathfinder, a technology demonstrator mission, was being worked on. And in fact, the last year has been a big year for us. Pathfinder was actually launched in December 2015. This is actually a picture of the launch, which was very nerve-wracking. It's not, again, like a sort of manned launch. Nothing happened slowly. The spacecraft shot off, disappeared. All went well. In fact, it went very well. And last year, again in the summer, the results from that technology demonstrator mission came back, and they were excellent. You can see there, meeting the requirement for the mission, in fact, beating it by a factor of 5, and demonstrating the technology, again, a sensitivity close to what was originally foreseen for a space-based mission. So again, the Pathfinder mission was a big success, and a gravitational wave mission is an earmarked future launch in Europe. And I haven't talked much about the technology. I'll just note that both for the space and the ground-based instruments, the technology spin-offs and the innovation that comes with doing the technology for this kind of science is significant. And the work on the ground has influenced, again, our thoughts, our understanding of what science we can do between the space and the ground. This is a recent paper from colleagues in Birmingham, who, again, having seen that we again detected these black holes colliding, these stellar mass black holes here on Earth, actually, it may be possible that with a space-based mission, we would see the early in-spiral phases of those black holes and be able to predict where and when those black holes would actually merge and be picked up, that merger be picked up potentially years later with detectors on the ground. So this has opened up, again, new thoughts about what science we could do, combining space and ground-based instruments and with the future SKA, LSST, again, exciting electromagnetic facilities to track the history of these objects. So, to finish up, we have this network that's coming. We've made first detections of the ground, on the ground, with ground-based instruments. A mission launch maybe could come forward again for a future space-based instrument to give us this set of instruments to study the gravitational universe. And we need new physics. We need new ideas in the area of gravity. Because again, as many of you probably know, the universe and what makes up the universe, the atoms, the stuff that we understand, actually turns out to be a small fraction of what we believe is out there, which we can sense through gravitational effects. We see objects in the universe moving in a way that suggests there is something there that has gravity, but it's dark. We call it dark matter, we do not know what it is. We can tell again that not only is the universe expanding, galaxies are moving apart, they're rushing apart, they're accelerating apart. We do not understand why. We see dark energy is causing them. We don't understand what that is. We need new physics, and particularly in the areas of gravity. Every time we've turned on a new telescope, in addition to the things we understand, these are all, again, pictures of the sky by different electromagnetic wave bands, and it looks completely different. Unexpected